In the discussions of the postulates in quantum mechanics, I have already discussed the postulate number 1, in which how the quantum mechanical operator of a physical property could be constructed. And for that I have already told the physical property to be expressed in terms of this position and momentum. And next, the position and momentum are to be replaced by their corresponding operators. And this in this second postulate, in a system there are some properties which will remain constant independent of the number of measurements, and this precise and exact value of these properties of the system could be calculated by using the eigenvalue equation. When some property does not satisfy the eigenvalue equation, then or when the property will give a variations of this measured value, then we tried to get this average value or expectation value of that property. In the fourth postulate, it is the time dependent Schrodinger equation. This equation, this postulate, as earlier as like the previous ones, could not be proved and also could not be derived, but these postulates form the basic format of this quantum mechanics. This time dependent Schrodinger equation, also taken as postulate, and it is taken as granted, and this one actually h cap and psi equal to I h cross del psi by del t. This h cap is the energy operator and call this a Hamiltonian operator. And this operator is equal to minus h square divided by twice m mass of this system into del square plus v cap. This del square is called Laplacian operator, and this one equal to del 2 by del x square plus del 2 by del y square plus del 2 by del z square. And this v cap is the operator of potential energy of the system, and every system has its particular value of this potential energy, and this potential energy here does not depend on time, but it depends on the space coordinates. Means x, y, z, space coordinates. However, if the force operating in the system depends on time, then potential energy will also vary with this time. And the next one, This psi is the wave function of this system. It is function of space coordinates x, y, z and time t. And this one, del psi by del t, is the first derivative of this psi with respect to time. So this equation contains the first derivative of this psi with respect to t. So single integration of this one would give the time variation of this wave function. Wave function, we know it defines the state of this quantum mechanical system. So this time variation of this wave function means if we know the value of psi at a given time, then value of this psi could be obtained in another time. Or I can say, if the future state of this quantum mechanical system can be predicted from this initial quantum state of this from this equation. Suppose psi 1 is the wave function or the state function in time t1, then psi 2 is t2. Then if we know this psi 1 at this time t1, then psi 2 could be calculated at a different time t2. This equation has a much similarity with this Newton's laws of motions. Newton's laws of motions in classical mechanics, for a dynamic system, its state is defined by position and momentum. And in Newton's laws of motion also predicts some future state or future position and future momentum from the initial state of this dynamic systems. Say, suppose position and momentum could be determined after some time interval. So say position, in case of positions, S equal to ut plus half at square, where a is the accelerations, and here this v velocity equal to initial velocity plus a the initial. If we multiply this one, then mv equal to mu plus ma into t. So this one is the momentum at the after the time t, and this one the initial momentum, and ma mass into acceleration gives this force operating on this dynamic systems. So in both the cases, Newton's second law of motion, Newton's laws of motion, and Schrodinger time-dependent equation, both are similar in nature, and this is why the Newton Newton's laws of motion may be called the quantum mechanical analog of this Schrodinger time-dependent equation. Only the difference is that the Schrodinger time-dependent equation predicts the future state, predicts the probable state, but the Newton's laws of motion actually predicts the value definitely. And here also we can determine the if we know we can determine the future state of this quantum mechanical system if the potential energy known to us, and in this case also the future state of this dynamic system could be determined, could be calculated from this force operating on this system. Only the difference is that the quantum mechanics gives the probable state, and the classical mechanics, it is a part of this classical mechanics that predicts this state definitely. This time-dependent Schrodinger equation, where this psi depends on x, y, z and time. So, if we consider the x coordinate only, the system is moving along this x-axis, then psi will be a function of x and t. So, this equation becomes in that case minus h cross divided by twice m into d2 by dx square plus v also v depends on this x, and here psi xt, and this is equal to I h cross this one del and del psi xt and divided by del t. However, this equation can be converted into the Newton's laws of motions, taking this h tends to 0. It is given for the students to do some mathematical exercise for the conversions of this time-dependent Schrodinger equation to this Newton's laws of motions, as I have already discussed in case of black body radiations, how the Planck's equation for the black body radiations is turned into the Rayleigh equations. Rayleigh equations is derived from this classical mechanics, and Planck's equation derived from this quantum theory. Both becomes equal when h tends to 0. So the students may be requested to do some intellectual exercise for this conversions. This equation, it is the time dependent Schrodinger equation in x directions and this time t. So this equation could be separated into two parts. One part is the space dependent and other part is the time dependent. If we put this psi xt equal to psi x into psi t, it is the product of these two, and these two are independent to each other. And if we put this psi xt here and do this mathematics, then the result becomes like that: minus h cross divided by twice m And whenever this psi xt is differentiated with respect to x, then psi t remains fixed, and it will be del 2 psi x divided by del x square plus v cap x, and here this psi x into psi t, and this one equal to I h cross, and here also differentiating this one with respect to time, then psi x remains constant and del psi t divided by del t. And whenever now dividing by psi x and psi t, we are having minus h cross square divided by twice m, and it is 1 by psi x, and it is del 2 psi x divided by del x square plus v cap x, and this one equal to I h cross, and 1 by psi t and del psi t divided by del t. This left hand side of this equation varies with x, and right hand side varies with t. So this equation could be equal whenever each part becomes a constant, and energy consideration shows that this constant will be the energy term, and let it be E say. Then these two equations could be separated, and the first one minus h cross square divided by twice m into 1 by psi x into del 2 psi x divided by del x square plus v cap x equal to E. Or we can write minus h cross square divided by twice m into del 2 psi x divided by del x square, or better let it take common, and plus v cap x, and this psi x is taken common, and this is equal to E psi x, and this is space dependent part of this equation, and similarly right hand side I h cross 1 by psi t into del psi t divided by del t is also equal to E. So better whenever we are separating the single variations, so del square we can write d square, and this is also d, and this is also d, and this is also d, whenever the single variable is there, and this is also d, and this is d into E. Or I h cross d psi t divided by dt equal to E into psi t, and this is time dependent part of this equation. And from this equation it is very interesting to know that this part is the operator and this is the eigenvalue and this is the function. This is the function. So this function, eigenfunction of this operator I h cross d by dt and with the energy value E. So energy operator, another energy operator you can write I h cross d by dt. When psi depends on time, this energy operator can be utilized to find this value. This separation of this time-dependent Schrodinger equation is possible when this V potential energy only depends on space coordinates and does not depend on time. And now I may again proceed to make an expressions of this psi from this equation to time dependence part. And this psi x could not be expressed as the V potential energy varies from system to system. So this solution of time dependent solution of a time dependent part of this equation. It is I h cross and d psi t divided by dt equal to E psi t. So psi t, we can write this as d psi t and divided by psi t equal to E by I h cross into dt. If we integrate this one, and this one is constant within the bracket, so it will be ln psi t equal to E t divided by I h cross plus ln a. Ln a is some integration constant. Taking this ln a left hand side, we have psi t equal to a into e to the power E t by I h cross. This is the expressions of this psi t. Then psi x t, expressions of this wave function for the time dependent Schrodinger equation is psi x into a e to the power E t divided by I h cross. Now I shall try to define the stationary state. Stationary state. Stationary state is also analogous to this standing wave in classical mechanics. In classical mechanics also I have shown this phi equal to twice a sine a pi x by lambda and into cos twice pi nu t. Nu the frequency, lambda the wavelength, x is the displacement of this wave at t the time. In this case also we have seen this amplitude will vary with the time but the maxima minima of this wave will not change with this time. Similar here also, instead of phi, this psi xt is equal to psi x depends on this position and a into e to the power e t by I h cos. Here also the psi xt depends on t, but the probability density at a given point will remain independent of time, like this one. And also energy of this system will also remain time independent. That we actually stationary state always defined by a wave function which is a product of the two terms, and one term is dependent on space coordinate and other term is dependent on time. And whenever the wave function of this state could be expressed in this way, that state we call the stationary state. I can also prove that the probability density psi xt modulus square, we can write here the psi xt into psi star xt, as it is the imaginary wave function. So instead of writing this psi xt, it is psi x and a into e to the power e t divided by I h cross into here also psi star x, complex conjugate of this x. We do not know the expressions of this psi, as potential energy is not known to the system, and so it is a e to the power minus e t by I h cross. Then it will give a square into psi x into psi star x. It means that this probability density at a given point remains time independent, at a given position remains time independent. I can also show the energy of this stationary state remains also time independent, as I h cross and d by dt, and here we can write a psi xt, and this will give this I h cross and d by dt, and here instead of this one we can write psi x into a into e to the power e t by I h cross. Whenever we are differentiating this one, I h cross and psi x into a into e to the power e t divided by I h cross, and when we are differentiating the time, it will give also e divided by I h cross. This I h cross and this I h cross will be cancelled and gives this value e into psi x into a into e to the power e t by I h cross, and this is equal to e psi xt. That means the psi xt is the eigenfunction of this operator, with an eigenvalue e, and since it is eigenvalue, constant value, so it will not depend on temperature, depend on time. So this is all about this time dependent Schrodinger equation. In my next class, the grammar or the rules and regulations of this quantum mechanics already completed, and next class I shall discuss the applications of the quantum mechanics, and first application, I will study the particle in one-dimensional box. In all respects, full details, I shall discuss that application, how the wave function could be determined for this particle in one-dimensional box, different properties and the energy values, and lastly I shall show how the Heisenberg uncertainty principle could be derived from this particle in one-dimensional box expression. That's all, and I thank to all who are watching this video.